Evening all, and welcome back to the WTF Shack. And as promised, we're going to continue this series of enlightening videos on vacuum tubes and how to get started with valves, and if you want to build a project, you know, where to start and how you do it. So the last video, which sort of basically looked at general principles of how a vacuum tube worked. So what we're going to look at this evening is power supplies for valves or vacuum tubes, because one of the important things you have to realise is that if you're building stuff with valves, as I mentioned in the last video, whatever you're building, be it a radio or a amp or a transmitter, the circuit is one thing which you've got to get your head round, but you've also got to factor in the power supply. So what we're going to do is give you some practical tips and just some general ideas of how to go about building a power supply, and also some safety things as well, because obviously things with valves, obviously they use fairly high voltages. What I'm going to be doing is the information I'll be giving is really sort of very practically orientated. I'm not going to go too much into the theory of things. There will be a little bit, but very, very little. But this is really sort of top tips, general practical guidelines as to what you need to get started and how to sort of build something up which is fairly safe, and hopefully you won't get zapped, or worse still, you know, bite the dust, or God forbid. Anyway, let's crack on and we'll show you some of the power supplies and a bit of information. Right, so when it comes to transformers, I've probably got one of the world's largest collections of transformers here. Got a few modulation transformers, high voltage, low voltage, you name it, I've got it here. So I think we should be able to find a couple here that we can show you, sort of demonstrate a few principles when it comes to building valve power supplies. Right, in front of us we have a typical mains transformer, high voltage or HT transformer, and this thing came out of a signal generator unit which had a load of valves in it, and it really illustrates some of the points. In fact, it really illustrates what a typical high voltage or HT transformer or valve transformer looks like. So if you look at the primary, this is the primary down here, and I hope you can see that. The light is a little bit flaky here. I'll just turn those off, it might make it a bit easier. Does it? No, not really. Anyway, so I'll just bring it a bit closer. So those two terminals there are for your mains, 240 volts. This one also has a couple of tags for lower voltages, and that's often quite common in a lot of mains transformers, certainly the older ones, which is what we use. So you've got 0 to 240 volts where you put your mains, and that's the primary. Now if we look at the secondary, again you probably won't be able to see, there's not much writing on this particular transformer. I'll bring it up so you can have a look. But we get it into the light. So you'll see there's a number of tags here, and this is really very typical. So you've got a number of windings here. The main winding is this from here to here, and I know that what the voltages are on here because I've measured them, but normally most transformers will actually tell you what it is, and I'll show you a transformer which does that. So typically a valve transformer will have a center tap, which is you can call it 0, and then it will have the high voltage on either side. So this one, for instance, will be, say, 300, this is 350, this is 350, or say 275, I should say, say 300, 275, 275, 300, something like that. And it doesn't necessarily have to be those voltages, and some transformers it's different depending on what valves it's using. So for instance, if it's a transmitter, you might find something like 450, 300, 300, 450. So you can play around with the voltages What you also have as well, very commonly, are the LT windings, low tension windings, for the heaters of the valves. And this one's got, as you can see, the LT windings are much thicker than the HT, and that's what gives you the clue. So these are usually 6.3. Sometimes they might be 2.5. I haven't actually measured the ones on this. I know one of them's 6.3, and I think one of them's either 2.5 or 5. And the 2.5 or 5 is usually for a rectifying valve, because back in the day they didn't really use semiconductor rectifying diodes like we use today. So the windings, the other secondary windings, the LT windings, are usually for the 6.3 for the valves in the actual circuit, and you also get 2.5 or 5 volts or whatever for the rectifier tubes, which for purpose of simplicity we're not going to really talk about, because the power supply that we will build for this demonstration will be a semiconductor, using diodes. It just makes things a lot easier. And as you can see here, I have a little power supply that I've made up. Try and zoom in a bit there. So I've actually got a bridge rectifier, and we'll draw this out for you using some diodes, and these are the 1N4007s commonly used, and I've got a capacitor there which is 150 microfarad at 400 volts. And I actually use this little board as a little test circuit, so if I want some high voltage for testing stuff, then I'll use this transformer. Anyway, let's just show you another example. So I've got another big transformer here. I'm going to hold it up because it is quite heavy. I'm not sure if you can see the writing there. Just turn it slightly. I'm going to have to put it down because it freaking weighs a ton. Anyway, I'll tell you what it is. It's this thing I think came out of a very large oscilloscope actually. So what you've got here is a 950 volt at 5 milliamps, which probably would have been for the actual tube, the anode, which 950 at 5 milliamps is not really much you can do with, I'm afraid. But the other two windings, 430, sorry, at 190 milliamps. So that actually, this transformer would be quite useful for something, quite a pokey transmitter. And we've got the primaries here, a 115, 115, and a screen. So you can tie these, put the mains across those two, and you can get 230 volts. Okay, so let's just have a look at this sort of on paper and see how we put all this together to make a power supply. So let's take a look at a sort of standard circuit for a high voltage power supply, and for sake of argument we've got a 250 250 secondary on our HT transformer, and there's different options here obviously. So let's say we want to have the HT, we want to get some HT for something like an 807. We want sort of around about 600-700 volts. So with this circuit arranged like this, you could easily do that. So what we've got here, we've got a bridge rectifier. Now I don't really want to go into the principles of diodes and rectifications because that's a sort of a video in itself. So if you're not familiar with how diodes and bridge rectifiers work, then it might be worthwhile just sort of Wikipediaing it or whatever. But I'm assuming a little bit of knowledge about this. So this is a bridge rectifier, 4 diodes arranged in a square, and these diodes typically would be something like a 1N4007. You could use something like a 1N5608, I think it is, which is a sort of meteor version of this. Probably if you're going for something like HT of 700, probably might be a good idea to use slightly bigger bigger diodes, but these are fine. I've used these and it works. So what we've got here is a bridge rectifier, and it's obviously across the whole winding. Now if you obviously wanted 250 volts, then you would obviously put the AC input between 0 and 250. So this is just one way of doing it. And I'm going to show you the alternative way of doing this if you want 250 volts. So let's say we want 500. So obviously the B positive is at the end of those two diodes there. And the next thing we have to do in order to filter the DC that's coming out of here, because otherwise if you don't use any capacitors, then you're going to get a very ripply output, which is going to be as useful as a chocolate fire guard. So you have to put capacitors. So rule of thumb, generally for HT voltages, let's say this is for a transmitter, you don't necessarily need to have a choke here if you've got enough capacitance. Now I use anything up to 10 to 50 microfarad, and that usually works fine. 50 microfarad is the, I mean, I have used even higher, but somewhere in that ballpark usually works fine. Obviously we'll talk about chokes in a minute, but with that arrangement there, and the other thing you have to pay attention, there's two things you have to pay attention to, is the working voltage. So this capacitor here needs to be 10 to 50 microfarad, for safety purposes about 1000 volts. Now if you didn't have that and you're running an HT of say 700, don't forget that the voltage that comes out of here won't be 500 volts, it's going to be 1.4 times the voltage across there, because it's a bridge rectifier and a capacitor. If you've got this arrangement, full wave rectification with a bridge, the output is 1.4 times what your transformer's providing. So that's important to remember that. So you've obviously got to factor that in when you're choosing your capacitors. So you've got to pay attention not only to the value, but also to the working voltage. Now if this, for instance, was supplying 700 volts, you could probably get away with maybe 800, 900, but it is pushing the limit, the safety limit a bit. Most capacitors are pretty good. I mean, I've used capacitors up to their working voltage and haven't had any problems, but for safety purposes, if you're running 700 volts, you probably want about 200 or 300 volts leeway, so you're looking at 10 to 50 microfarad at 1000 volts. So if you're looking for a capacitor that's 10 to 50 microfarad, let's say 10 microfarad or even 50 microfarad at 1000 volts, you ain't going to find one of those very easily in RS or Farnell. Okay, so you're going to have to use a bit of imagination. And what we do here is we just string the capacitors in series. So obviously the more capacitors you put in series, the less capacitance you have, but the more working voltage you have. Okay, now in very, very high voltage supplies, we very often, for instance, in my previous videos, I think the video with the 3500Z linear amplifier, I mean that power supply goes up to 4 kV, and we've got something like 10 or 12 of these capacitors all strung in a big long line in series to give us the capacitance and the working voltage. The other thing which you're going to do as well is you need to put bleeding resistors across these capacitors. Now again, rule of thumb, usually for a supply of this size I generally go for 100k at 2 watts. Now if you want to do the maths and work it out, you basically need to work out the resistance with a bleed current of about 5 to 10 milliamps. Okay, obviously the higher the bleed current and the quicker your capacitors will discharge, but then you're going to need a much more bigger, you're going to need a bigger resistor. And for practical purposes, getting big resistors, which you're talking about wire wound resistors, to bleed off the current becomes a bit difficult. So I usually go for this voltage, 100k, 2 watts, you can usually find them quite easy. They're easy to get hold of from the electronic suppliers. And best practice is you generally put a resistor across each capacitor. That also balances the voltage across each capacitor as well, so the whole thing works a lot better. So that will give you, that design on its own will give you 700 volts, perfectly smooth, rectified, and you won't need anything else. Now if you want to be, now for transmitters such as an oscillator or a PA, RF amplifier, this type of arrangement is usually sufficient. Now if you're talking with audio where you've got, possibly you're dealing with lower voltages, perhaps 250, and we'll show you a typical audio voltage HT power supply, you probably won't get away with just having capacitors only. You're going to need a choke, a filter choke, and we'll talk about that in a minute. But as I said, this arrangement will work for most things like 807s, 6146s, GU50s, anything you want to put a bit of HT, power amplifiers of a transmitter. This type of power supply will work. And you don't want to go overboard with the capacitance. You don't need anything more than 10 to 50 microfarad. If you start going overboard, then what will happen is you have too much. Then you start getting too much current going through this capacitor, and for instance, it doesn't really sort of add that much to your smoothing. It's not really necessary. So yes, you can increase the capacitance, but it's not really necessary. And the other thing as well, when you're dealing with these sort of voltages, sort of anything above, I would say 100 microfarad, what this rectifier sees when you first switch on is almost a dead short because of that huge capacitor, and that will start tripping your fuses and all the rest of it. So it's not necessary to go overboard with this smoothing capacitor. This value is usually perfectly adequate. So with that, we will just take another look at an alternative arrangement to a bridge rectifier, which is also commonly used in valve circuits. And we'll talk about the choke, because I think the choke is quite an important thing, which is often seen, in valve power supplies. Right, so this is the other arrangement that you probably see in valve power supplies. And again, we're using the same transformer, 250-0250, but in this situation we don't want 700 volts plus, we want, say, 250, perhaps to supply the anodes of, say, a preamp stage or a driver, something like a 6BW6 or a 12BY7, something like that, which very often uses an anode voltage in the region of, say, 250 volts. Now, if this, for instance, was an audio amp, one of the things you will need to do is filter it a lot more carefully. So in the previous circuit I showed you that we just had a capacitor on the output, which for high voltages, providing it's sufficient value, is usually adequate. But if you're doing it with audio, or if you're using slightly lower voltages and you want better filtering, then you have to use what's called a choke. And a choke is basically a big inductor, and for power supplies you're usually talking of a value between 8 and 20 henries. Okay. The problem with a choke is that it has resistance, so it's obviously limited by how much current it passes. So for a power supply like this, say, which is maybe supplying at the most, say, 50 milliamps, a choke like that is usually quite manageable, and they're quite readily available from the various electronic sources, DigiKey, Mouser. Hammond make a whole load of these chokes, which are quite nice, but sort of HT supplies in the sort of 200 volt region. So what you'll notice as well is, compared to the other circuit, is that we haven't got the square of diodes. We've just got 2 diodes on each leg of this transformer, and we've got the center tap grounded. So this is full wave rectification, just like the bridge rectifier, but what you've got here is the centre tap goes to ground. Now a lot of valve power supplies which used tube rectifiers basically use this arrangement, and that's one of the reasons why when you look at your HT transformers or your vintage HT transformers, what you'll find is that the HT power supply is usually 250/0250, so that they can, you know, use half-wave rectifying tubes, because otherwise if you wanted to put a bridge you'd have to use 4 tubes, and that just makes a bit of a nightmare. So that's the reason why I did it like this. And in terms of the filter capacitors, again, you don't probably need anything more than 10 microfarads if you're using a choke, and this will produce a very good filtered DC at about 250 volts. One of the effects of the choke in a high voltage power supply is that it tends to sort of stiffen up the power supply. So one thing you'll notice is if you're just using a capacitor here on the output of this power supply, what you'll find is that you tend to get the voltage going all the way up when it's off load. The choke, what you find is that it sort of stiffens the thing up a bit, so that the offload voltage and even the onload voltage is a bit lower, and you get filtering. You get rid of all the ripple, well, most of it anyway. So that's in practical terms, those are more or less the two sort of circuits that we use for high voltage power supplies. Now, if you're using low voltage power supplies, let's say for the heater supply, you could use something similar to this. But in general, most of the valve heaters are generally run off AC, but sometimes you do have to use DC. For instance, in some audio applications, you might find that you're getting a bit too much hum. And DC supply is very similar. We don't usually use a choke; it's not that necessary. You can if you want, but for most time, for DC supplies, you use a bridge rectifier or something like this. But you use a much larger value capacitor, so something like 10,000 microfarad at so let's say if it's 12 volts, something like 24 volts, 25 volts. If it's 24 volts, you're using maybe 35 volts working, something like that. So that's the difference between the LT supplies and the HT, but I'm going to be concentrating mostly on HT supplies. Right, so let's look at some practical designs and some of the sort of practicalities of building something like this. Okay folks, what we'll do is we'll leave it there. I had thought about putting all this on one video, but I think it's getting a bit too long. So in the next section or sequel to this, we'll look at some practicalities of building valve power supplies, and we'll give you some examples of some of the well, at least one power supply that I've built, so you can sort of see the way they're put together. Anyway, till the next video, thanks for watching.